Welcome back to BrewFix, where coffee meets craftsmanship. And today we're going deeper than recipes, deeper than pressure gauges, deeper even than extraction yield. Because if you strip espresso down to its physical reality, you discover that it is fundamentally governed by particle chaos, a concept rooted in the very physics and chemistry of ground coffee. When a roasted coffee bean fractures under burrs, it does not shatter into uniform spheres, but into an irregular spectrum of particles. With wildly different sizes, shapes, densities, and internal cell structures. And, as described in espresso science literature, this particle size distribution is not a flaw of poor equipment, but a structural inevitability of brittle cellular material breaking under mechanical force. Larger particles retain intact cell walls and extract slowly as water diffuses inward before solubles dissolve outward, while fines, often below 100 microns, expose ruptured cell interiors and release compounds almost immediately, meaning that before water ever touches the puck, the chemical timeline of extraction has already been fragmented into thousands of competing microevents. When hot water at elevated pressure is introduced, it does not bathe the puck evenly, but percolates through a deformable porous medium whose permeability changes second by second as particles swell, gases escape, soluble solids dissolve, and structural collapse begins. And fluid dynamics tells us that flow through such a medium is inherently unstable because minute differences in resistance amplify under pressure, leading to preferential pathways, localized channel formation, and constantly shifting velocity gradients that no machine can perfectly regulate. This means that some regions of the puck experience accelerated extraction, dissolving acids and later bitter phenolic compounds at higher rates, while adjacent regions remain comparatively under-extracted, preserving cellulose structures and trapped solubles that never meaningfully contribute to the cup, creating a layered beverage composed not of uniform balance, but of averaged extremes. Furthermore, espresso's short contact time intensifies this imbalance because extraction kinetics are nonlinear. Acids and small aromatic molecules dissolve rapidly. Sugars and lipids require sustained contact and stable flow. And late-stage compounds, such as chlorogenic acid derivatives and certain astringent phenols, surge disproportionately when flow accelerates in weakened zones. So what we perceive as sweetness, body, and bitterness is actually the sensory integration of these asynchronous dissolutions occurring across thousands of particles simultaneously. The book makes clear that extraction yield as a single percentage conceals this internal variability, because a shot can register a desirable average extraction while still containing pockets of severe over and under extraction. And this hidden heterogeneity is the true reason why, too. Shots pulled under identical macroscopic parameters, same dose, same temperature, same pressure, same time, can still diverge subtly in taste. Pressure itself, often mythologized as espresso's defining force, does not homogenize this chaos but magnifies it, because increasing pressure increases velocity differentials between low and high resistance zones, exacerbating microchanneling and redistributing fines mid-extraction, effectively reshaping the puck as the shot progresses. Even thermal stability, while critical for predictable solubility rates, cannot equalize particle-level differences because temperature affects dissolution kinetics uniformly but does not alter the physical heterogeneity created at the grinding stage. What emerges from this scientific framework is the understanding that espresso is not a precisely choreographed chemical ballet, but a managed disorder. A system in which the role of the barista or technician is not to eliminate chaos, but to constrain its extremes by narrowing particle distribution through burr alignment and maintenance, minimizing fines production, ensuring consistent puck density, stabilizing water chemistry to maintain predictable extraction behavior, and keeping mechanical systems clean so that external variability does not compound internal instability. Paradoxically, it is this very particle chaos that gives espresso its complexity and depth, because the slight misalignment between early acidity, mid-palate sweetness, and Late bitterness creates dimensional flavor rather than flat uniformity. And if extraction were perfectly even across all particles, an impossibility in porous flow systems, espresso would likely taste monotonous and sterile. Once you internalize that espresso is governed by particle chaos, you stop obsessing over minor fluctuations in shot time or pressure readings and begin focusing on system stability, grinder condition, and flow integrity, understanding that what matters is not perfection, but controlled variability within a narrow, delicious range. And this shift, from chasing mythical uniformity to managing real physical disorder, is what transforms espresso from a frustrating ritual of endless tweaking into a coherent, logical process grounded in physics, chemistry, and engineering reality, which is exactly what we aim to teach here at BrewFix, where we don't romanticize espresso as magic, but respect it as a dynamic system of particles, pressure, heat, and time, all interacting under constraints that no machine can fully tame, but that skilled hands can guide toward balance. Because once you see espresso for what it truly is, organized chaos averaged into a cup, everything about dialing in, troubleshooting, and maintaining your equipment finally makes sense. Wrench BrewFix, keeping your coffee machines running and your mornings caffeinated.